Okay, so we're moving on to static rigid bodies. I apologise, it's taken me a long time to get this video up to you. I've filmed it, or tried filming it, on several different occasions, but my phone storage just kept being full. I've deleted things, it's still full, so it's taken me about an hour and a half to try and get this done. But hopefully, this is it now. So, the fact we're dealing with a body now, a rigid body means that we can also look at moments. So what we've got to remember for a static rigid body, when it's in equilibrium, it's stationary, the resultant force in any direction is 0, and the resultant moment is 0. So moments are the magnitude of the force multiplied by the perpendicular distance. Now, in some circumstances, finding the perpendicular distance can be quite challenging. So in some of the examples I'm using, I'll be looking at the force as a perpendicular, so where it's meeting the perpendicular to the distance. So the distance is multiplied by the force meeting the distance at a perpendicular. So you'll see what I mean when I'm looking at resolving them on an inclined plane. I just think it's actually quite a bit easier to picture it, whereas sometimes finding the perpendicular distance, depending where it meets, can be really quite hard. So I'll show you what I mean when we get to it. So, first example. A uniform rod AB of mass 40 kilograms and length 10 metres rests with end A on a rough horizontal ground. So my rough ground, my rod AB. So the fact that it's uniform means that the mass is in the centre. Now I'm not going to write the measurements on just yet because I've got a couple of other things to put in the question first. The rod rests against a smooth peg C, where AC is 8 metres. So I note that's 5 and 5 because that's in the middle. If it's 8 metres, that must be 3, and then that's 2. The rod is in limiting equilibrium, so it's on the verge of movement, at an angle of 15 degrees to the horizontal. Find the magnitude of the reaction at C and the coefficient of friction between the rod and the ground. So the first thing I need to do is add on my forces. I've obviously done my weight. I have a normal reaction at C because it's resting at C, and I have a normal reaction at A as well because it's resting at A. Now if this body were to move, the only way it's going to move against the ground is going to be that way. So that means friction must be acting in that direction. Okay, so we can get started. So A is to find the magnitude of the reaction C. So my choice here is I can either resolve forces or I can take moments. Now, it's not really going to be sensible for me to resolve forces at the moment because I've at the moment got 3 unknowns, okay? So if I resolve any of these, for a start I've either got to resolve horizontally and vertically, which makes this difficult, or I've got to resolve perpendicular and parallel, which makes these difficult. But either way, I'm not going to solve for this. So instead I'm going to take moments. Now I can take moments anywhere where there might be movement, or sometimes it's called slippage. So I can take a moment at A or a moment at C. Now I want to find the normal reaction at C. So if I take moments at C, then that doesn't matter, that doesn't count. So I don't want to take moments at C because I need to calculate this. So I'm going to take moments at A. It also means I don't have to worry about the normal reaction or friction. So it eliminates my other 2 unknowns. So moments at A. So my moments clockwise. So if I was tilting at A, what's going to make it tilt clockwise is going to be the weight pulling it down. Now this is where I've sort of changed tactic. Distance multiplied by the force at the perpendicular. So that is the perpendicular meeting between distance and the force. It's just that instead of me writing the modulus of the force times by the perpendicular distance with the sine or a cosine. I'm doing the distance meeting the perpendicular resultant of the force, which is 40g cos 15. So this is why mine's slightly different to the book, because the book has written 40g times 5 cos 15, but the diagrams don't tell you where those perpendiculars meet, because they are quite difficult to visualise. So this is exactly the same answer, it's just that I've used laws of multiplication to swap those around. So my clockwise moments are 200g cos 15. My anti-clockwise moment, so the thing that's going to make this tilt this way, must be my normal reaction at C. So it's 8 metres away and meets a perpendicular, so it's 8 lots of the normal reaction. So therefore, because it is limiting equilibrium, the moments in both directions must be equal because there is no movement. So therefore the normal reaction is 200g cos 15 divided by 8. 236.65 blah blah blah. I'm likely to need to use this later because I have 2 unknowns, so I need a number of decimal places. But 237 newtons to 3 significant figures. Okay, so now moving on to part B, which is to find the coefficient of friction between the rod and the ground. So we are going to need to find something for F and something for the normal reaction, either its exact value or something in terms of the other information we've got. Because I'm in limiting equilibrium, I know that I've got friction at its maximum, which is equal to mu r. Now, in my diagram, before I move it up too far actually, my normal reaction at A and my friction are vertical and horizontal. My weight is vertical, but my normal reaction is perpendicular to the inclined plane. So I've got a number of forces acting in different directions. Now normally with inclined planes we would use the parallel and perpendicular. However, if I have to form the parallel and perpendicular of friction and the normal reaction at A, I end up with 2 really quite complicated simultaneous equations. And whilst it is possible to rearrange to make the normal reaction at A equal to something in terms of F, or friction equal to something in terms of the normal reaction at A, it is really quite difficult. So I'm going to choose to resolve vertically and horizontally. Now that also means that I only need to deal with that force which currently isn't vertical or horizontal. So rather than, like I would here, drawing in my perpendicular and parallel to the plane, I'm going to draw in my horizontal and my vertical here. Now the difficult thing is, what is the value of this angle? Because we are doing a lot of parallel lines and it is quite difficult. So what I'm going to do is I'm just going to do a little diagram when I got my piece of paper separate. So I'm just going to do a little diagram to the side of my inclined plane of 15. So I've got my normal reaction here, and I've got my other forces there. So if I just do a dot, dot, dot there. So these lines are parallel. So if you use angles in parallel lines, this one must be 15 degrees. Now I know, because this is perpendicular to the inclined plane, this whole angle is 90 degrees. So therefore that angle there must be 75. So my diagram here, I can write that as 75 degrees. Okay, so it is possible that you will need to sort of do a couple of side drawings to help you. But now that we've got the information, we can calculate our resultant. So I am going to have to keep moving up and down the page, so I apologise. If you have your diagram in front of you, that'll be a bit easier. So I'm going to resolve horizontally first, doesn't matter, just I decided to. So I've got my horizontal force of friction acting in that direction, and that is equal to the horizontal of the normal reaction at C acting in the other direction, so it must be equal to my normal reaction at C. I'm just going to write it like that rather than writing out all the decimal places because it makes it easier when we're working, multiplied by cos of 75, okay? So that is going to be cos of 75. So I've got my value for friction, so I'm now going to resolve vertically. So I've got my normal reaction at A going vertically upwards. I've also got, because my normal reaction at C is generally a force going in that direction, the vertical force must be going up. So I've also got the vertical component of my normal reaction at C. And that is equal to, the only one going vertically down is my weight, 40G. Now I obviously want a value for the normal reaction at A, so 40G subtract the normal reaction at C, sine 75. Now I can substitute these in to my Fmax formula. So RC cos 75 must be equal to mu multiplied by 40G minus RC sine 75. Now I obviously know what RC is. It is really important that we use, I'd say, at least 5 decimal places. When I initially did this question, used it rounded to 3 significant figures, and my accuracy was out. So you do need to use quite a few more, but 5 gave me accuracy to the same level. So you're going to divide this side by 40G minus RC sine 75, and then you calculate that mu is equal to 0.37 to 2 significant figures. I could have put 0.374, I think mine would have been, to 3 significant figures, but obviously we have got gravity, so if we do 2 significant figures, then it doesn't matter. Okay, so that one was the first of quite a challenging question. So let's see how we do with our second question. So a ladder AB of mass M and length 3A has one end A resting on rough horizontal ground. The other end B rests against a smooth vertical wall. So I like diagrams where it's easy to draw AB like that. So it has mass M and length 3A. At the moment we haven't been told whether it's uniform, so I can't add any of that information on yet, so I'm just going to leave it. A load of mass 2M is fixed on the ladder at the point C, where AC is equal to A. So I've got point C here, so that's the distance of A, and that's got a weight of 2mg. The ladder is modelled as a uniform rod, so that means I can put the weight of the ladder, mg, in the centre. So this would be 0.5a, and this would be 1.5a. And the load is modelled as a particle, yep. and it's a vertical plane perpendicular to the wall, so it's basically saying that the wall meets the floor at a right angle. The ladder rests in limiting equilibrium at an angle of 60 degrees to the ground. So I just need to make sure that I have all of my forces before I start answering the question. So I'm going to have a normal reaction at A. If the ladder were to move, again it would move that way, which means that I have friction acting in that direction. There is a normal reaction whenever there is anything resting. So this ladder is resting against the wall. The normal reaction is always perpendicular to the plane it is resting against, so that is going to be acting in that direction. There is no normal reaction at C. The mass is fixed to C. So it's not resting on top of, it is fixed, which effectively means it becomes part of the overall weight of the ladder. It's just, what this actually does is make the question, I suppose, a non-uniform rod. Even though the ladder itself is uniform, so that mass is distributed in the middle, the overall mass has a slightly odd distribution. So you could think of it in that way. So there's no normal reaction at C because it is fixed. It is in addition to the weight. It's not resting, so it hasn't got a force pushing it back up. Okay. A. Find the coefficient of friction between the ladder and the ground. We have lots of unknowns, which means that actually taking moments on its own won't help us, and resolving on its own won't help us. So, therefore, we're going to need to do both. Now, quite fortunately, everything we've got is either horizontal or vertical. So our resolving is actually quite a bit easier. Choice colours. Now I'll just keep it black for now. I'm going to resolve horizontally first. So friction is equal to the normal reaction at B. It's in limiting equilibrium, so nothing's moving, everything's equal. Then going to resolve vertically. So the normal reaction at A is equal to 2mg plus mg, so it's equal to 3mg. So we can take moments at anywhere where there might be tilting, so we can take moments at A or at B. Now the question says that you want the coefficient of friction between the ladder and the ground. So I need these bits of information in my calculation, okay? So I'm going to take moments at B. So this is again where I'm going to start adding in all my perpendiculars to the plane. So I've got my perpendicular forces. So again, a bit like we did before, where I'm using, rather than a perpendicular distance, I'm creating a perpendicular force with the distance so that it is actually quite a lot easier for us to work out. So that is going to be going that way. That's got to be 30 degrees. That 30 is really small, but that 30 degrees just to convince you that it definitely is. And I've then got a force acting in that direction. Okay. So the book example it gets its cosine and its sine slightly different to me in a couple of cases. It obviously depends on where they've drawn it, but this all gets the correct answer. It's exactly the same, it's the right method, so please don't worry about it. So I need to do my clockwise moments. So B, what's going to make it go clockwise? And that's the moment going in that direction. So this normal reaction is a distance of 3a away, even though I've drawn my perpendicular here, because I could have drawn it there and it'd be the same, okay? So that might be why this one is slightly different. So it's 3a lots of the normal reaction sine 30. I then need to take my anti-clockwise moments. So I've got an anti-clockwise movement with my friction at point C and to do with my weight. So distance times by the perpendicular force in all of these. So I've got friction times by 3A sine 60. I've also got, this is 2A away, so 2A lots of 2 mg cos 60, and then this is 1.5A away, mg cos 60. So these are in limiting equilibrium, so this is going to be equal to all of that. Before I do, because this is going to be a lot to write out, anything I can simplify that I can get rid of, I would like to get rid of. Every single part has a factor of A. So when I make them equal to each other, I can remove that factor of A. I don't need that A value. I don't need to know its length. I want to get rid of any unknowns that I can. So, normal reaction, 3 sine 30 is equal to F3 sine 60. I know we'd normally write 3F, but I've done it that way around now. Plus 4 mg cos 60. Obviously, you've got the 2 times 2. Plus 1.5 mg cos 60. So I'm just going to collect my like terms. So, and I'm actually going to neaten it up because I don't like the 3 being afterwards. It's just me being picky. So 3 lots of the normal reaction of A sine 30 is equal to 3 lots of friction sine 60 plus 5.5 mg cos 60. Now, I've got 2 unknowns here, but as I worked out when I've resolved my values, I've got a value for friction and I've got a value for the normal reaction of A. Now, I still don't know M, so I have got an unknown there. So actually, substituting in friction is the normal reaction of B isn't very helpful. What I do know is friction is mu R. So friction must be equal to mu times by 3 mg. So that I can substitute in, and then I can work out the coefficient of friction. So I'm going to substitute in these 2 values for the normal reaction at A and for friction. So 3 lots of 3 mg is going to leave me with 9 mg sine 30. So as a reminder, I've substituted in the RA is 3 mg. And that is equal to 3 lots of friction. So 3 lots of 3 mg times by mu. So mu times by 9 mg sine 60. So I'm just reminding you that friction is equal to mu times by RA, and I've substituted that in, plus 5.5 mg cos 60. So obviously I want to get mu on its own, so mu is going to be equal to 9 mg sine 30, subtract 5.5 mg cos 60 all over 9 mg sine 60. I don't know m, but I've got m as a common component in all parts of my equation, so I can cancel it. Then I've got everything I know to just type all this into the calculator, and mu is therefore equal to 0.2 2, 5 to 3 significant figures. So that one is quite a challenging question, but you just have to approach it in the sense of, let's start by resolving, then let's take moments. What information have I got here that I can now use? Part B is just one of these where they like to challenge your understanding generally of mechanics and the questions that you're doing. So state how you've used the assumption that the ladder is uniform in your calculations. Well, we've kind of already said that when I was working through the question. The assumption I've made is that the weight is in the centre of the rod. And that's it really.